Welcome, students, to the captivating realm of physics, where curiosity meets discovery. As we embark on this intellectual journey, I encourage you to explore the wonders of the universe, from the smallest particles to the vast cosmos. I invite you to view our latest video, which delves deeper into this fascinating subject. Kindly subscribe to our channel for ongoing insights and discussions that will ignite your passion for learning. Together, let us uncover the mysteries of nature. AC circuit containing a resistor, an inductor, and a capacitor in series RLC circuit. Phasor diagram for a series RLC, circuit voltage and impedance triangle special cases.
Now let us consider an AC circuit which contains all the three components: a resistor, an inductor, and a capacitor, which are all connected in series. And this is called a series RLC circuit. First, let us consider a circuit which contains a resistor of resistance R, an inductor of inductance L, and a capacitor of capacitance C, which are all connected across an alternating voltage source given by V equal to Vm sin omega t. The instantaneous value of the alternating voltage is given by the expression V equal to Vm sin omega t. So this is the expression for that, and this is the components: resistance, inductance, and capacitance. Let us consider the voltages across the resistance is given by Vr, and that is by VL across the inductance and Vc across the capacitor. So this is the expression for the instantaneous value of alternating voltage. Now, if I be the resulting current in the circuit at that instant, because of that, the voltage is developed across R, L, and C, which are given by VR, VL, and Vc. We know that the voltage across R, that is VR, is in phase with the current I. And the voltage across L, that is VL, will lead the current by pi by 2, and the voltage across the capacitor C, that is given by Vc, that will lag behind the current by pi by 2. The phasor diagram is drawn with current as a reference phasor, and the current is represented by the phasor OI, VR by OA, and VL by OB, and VC by OC, as shown in 4.47 here. So this is the phasor diagram for a series RLC circuit. So VL is the voltage across the inductance, VC is the voltage across the capacitance, and the resulting voltage is given by Vm, that is the maximum voltage. The resulting voltage will be V, that is represented by the letter V, and VR is the resistance, and that is the voltage across the resistor, that is given by VR. So we have all the three components: VR, VL, and VC, for which the resultant voltage is given by V and the maximum voltage is given by Vm. And here we can calculate the length of these phasors, which are given by OI equal to Im, OA equal to IMR, and OB equal to IMXL, OC equal to IMXC. So this R is the resistance, and XL is the inductance, XC is the capacitive inductance. These are having all the same units as ohm: inductive reactance and capacitive reactance. XL is the inductive reactance and XC is the capacitive reactance. Now the circuit is either effectively inductive or capacitive or resistive, depending on the value of VL or VC. Let us assume that VL is greater than VC. That means the voltage across the inductance is greater than the voltage across the capacitor. Therefore, the net voltage drop across LC combination is VL minus VC, which is represented by a phasor OD. By parallelogram law of vectors, the diagonal OE gives the resultant voltage V of VR and VL minus VC, and its length OE is equal to Vm. That's the maximum voltage. Therefore, this square of Vm, that's given by square of VR plus VL minus VC the whole square. And from that expression, we get this expression for the maximum current Im equal to Vm by root of R square plus XL minus XC the whole square. That is R square plus XL minus XC the whole square is Well, the impedance of the circuit that is denoted by letters Z. Therefore, Im is given by Vm by Z. And this Z refers to the effective opposition to the current by the series RLC circuit. So this is the phase diagram for a series RLC circuit when VL is greater than Vc, and this is the voltage and impedance triangle when XL is greater than Xc. And this is these are the voltage triangle and impedance triangle. These things. Then from the phase diagram, the phase angle between V and I is found out from the following relation: tan phi equal to VL minus Vc by VR, and that's given by XL minus Xc by R. So this is expression for the phase angle between the voltage and current. Now let us consider the special cases for which the first case is when XL is greater than Xc. Here XL minus Xc is positive and the phase angle phi is also positive. Means that the applied voltage leads the current by phi. That means the current will lag behind the voltage by phi, and therefore the circuit is said to be inductive. Therefore, the expression for the instantaneous value of current is given by I equal to Im sin omega t, and the instantaneous value of the voltage is given by V equal to Vm sin omega d plus phi. Now let us consider the second case in which XL is less than Xc. That means XL minus Xc is negative and phi is also negative. Therefore, the current reaches the voltage by phi, or the voltage lags behind the current by phi, and therefore the circuit is said to be capacitive. And the instantaneous values of current and voltage given by these expressions I equal to Im sin omega t and V equal to Vm sin omega d minus phi. And in the third case, if the values of XL and Xc are equal, that means XL is equal to Xc, then phi is 0. Therefore, the current and voltage are in same phase with each other, and the circuit is said to be resistive. And instantaneous values of voltage and current are given by this expression V equal to Vm sin omega t and I is equal to Im sin omega t.